This is Epp section 4.5. So we're going to start with a couple of definitions. Given any real number x, the floor of x, and it is denoted so it's at the bottom, the little bits at the bottom remind you that it's the floor, is defined as floor of x is equal to that unique integer n such that n is less than or equal to x is less than n plus 1. So if we draw a little map, real number line, okay, here is n, okay, I'm going to have a closed circle there. Here is n plus 1, having an open circle there. And if x is anywhere in between here, then the floor of it is x, n. Well, the floor of x is n. We can write it symbolically. X, or the floor of x, is equal to n if and only if n is less than or equal to x is less than n plus 1. So, let's have another definition, a companion definition. Given any real number x, the ceiling of x and that is denoted the little ceiling parts here is defined as equals that unique integer such that n minus 1 is less than x is less than or equal to n. So if we have a little picture, here is n minus 1, here is n. If x is anywhere in here, then n is the ceiling of x. So if we had x is equal to 2.1, the ceiling of x, oops, be careful not to put brackets on both sides, is equal to 3. If x is equal to 2.9, the ceiling of x is equal to 3. If x is equal to 3, the ceiling of x is equal to 3. And symbolically, the ceiling of x is equal to n if and only if n minus 1 is less than x is less than or equal to n. I'll just put a little line there. So let's have a look at what we can do with these definitions. So we can say for all real numbers, x and y, the floor of x plus y is equal to the floor of x plus the floor of y. Notice we haven't written a theorem here for it. Is this true? Alright, well, let's have a think about it. If we have numbers that are close to, well, have got large fraction parts, so 4.9, 10.8, then the decimal parts are going to add up to be more than 1, so it's not probably going to work. So let's use, suppose x is equal to 4.9, y is equal to 2.6. The floor of 4.9 plus 2.6 is equal to the floor of 7.5, which is equal to 7. The floor of 4.9 plus the floor of 2.6 is equal to 4 plus 2, which is equal to 6. Okay, not equal. Therefore, we have found a counterexample to the statement above this one. Okay, it's not true. But what could we have that was true? This is theorem 4.5.1 on page 194. This is for all real numbers x and for all integers m the floor of x plus m is equal to the floor of x plus m. And we say, well, that is probably going to be true. Well, we've called it a theorem, so we're going to prove it is true. Because m is an integer, so it never has any decimal places, well, decimal parts. So it's always just going to get added on. So we will prove it now. So when we're going to prove something, always write proof. And suppose x is a particular, we might get tired of writing this soon, a particular but arbitrarily chosen real number. Remember, we could say let x be any real number. That means the same thing. And suppose m is a particular but arbitrarily chosen integer. Alright, let n be the floor of x. Okay, we're just calling the floor of x a name. So, by definition of floor, we know n is less than or equal to x is less than n plus 1. Now we're going to add m to all sides of the equation. All right, I'll write it again. N is less than or equal to x is less than n plus 1. Now add m to all parts of the inequality. N plus m is less than or equal to x plus m is less than n plus m plus 1. And we say, okay, so n and m are both integers. Okay, we've already said m was a particular one. N is the floor, so that is an integer. N plus m is an integer because integers are closed under addition. And so by the definition of floor, the floor, so here we go, the floor of x plus m is just equal to n plus m. Let me say n, but n, we've already said that is equal to the floor of x plus m. And that's exactly what we wanted to have. We'll put this here, x plus m. The floor of x plus m is just the floor of x plus m, as we wanted to prove it. Now, we're going to have another one where we're going to prove it by division into cases again. So, but let's have a think. What if we've got the floor of 4 divided by 2? Well, that's just the floor of 2, which is equal to 2, which is equal to 4 divided by 2. What if we had the floor of 5 divided by 2? Well, that's equal to the floor of 2.5, and that is equal to 2, which is equal to 5 minus 1 divided by 2. So, we're going to put that into a theorem now. That's just a little example to start to get our minds thinking right. So this is theorem 4.5.2. And that says for any integer n, the floor of n divided by 2 is equal to n divided by 2 if n is even, and n minus 1 divided by 2 if n is odd. Okay, so now we're going to do the proof, and we're going to do the proof by division into cases. Okay, case 1. N is odd. So we say, all right, by the definition of odd, n is equal to 2k plus 1 for some integer k. Alright, so the floor of n over 2 is equal to the floor of 2k plus 1 over 2, which is equal to the floor of 2k on 2 plus a half. Just dividing it up. If you have trouble with this, see me in MASH. This is equal to the floor of k plus a half, which is just equal to k. Okay, that's the right-hand side, this part here. Sorry, that's the left-hand side, this part here. Now have a look at the right-hand side. we have n minus 1 over 2, but n is equal to 2k plus 1 minus 1 over 2, which is equal to 2k over 2, which is equal to k. So they're both equal to k. Therefore, the floor of n over 2 is equal to n minus 1 over 2 when n is odd. Case 2. When n is even, n is even, therefore, by the definition of even, n is equal to 2k for some integer k. We have used k up here, but we've finished with that part, so we can start again and call this one k. We could call it L if we wanted to. So, this means the floor of n on 2 is equal to the floor of 2k on 2, which is equal to the floor of k, which is just equal to k. Okay, and by the definition of floor, we know that k is less than or equal to k is less than or equal to k plus 1. Okay, so this is all right. We also know that n on 2 is equal to 2k on 2, which is equal to k. Therefore, the floor of n on 2 is equal to n on 2 when n is even. So that completes our proof. Now we want to look back at the quotient remainder theorem and see how we can tie this in to the quotient remainder theorem. So, just a little reminder, the quotient remainder theorem, what the quotient remainder theorem actually tells us. So, quotient remainder theorem says, given any positive integer n and actually, yes, all right, given any positive integer n and positive integer d, I'm wondering if I should have positive there. Anyway, never mind, check up in the book. There exist unique integers q and r such that n is equal to dq plus r and naught is less than or equal to r is less than d. Okay. So we can write it up as to its quotient and its remainder. And what we said was the notation that we used at the time when we did this, we'll put a little line under here, n div d is the integer quotient when n is divided by d. And n mod d is the non-negative integer remainder obtained is divided by D. Now, but we can write, actually, I have a new piece of paper. So remember, we've got n is equal to dq plus r. Q is the, if we have n div d, that's equal to q. But q is equal to the floor of n on d. R is equal to n minus d times the floor of n on d. So let's have an example. For example, if n is equal to 43 and d is equal to 6. Okay, the floor of 43 on 6 is equal to 7. Because remember, 7 6s are 42, so there's just one left over. So r is equal to 43 minus 6 times the floor of 43 on 6. And that's equal to 7. 6 times 7 is 42. 43 minus 42, which is equal to 1. Because remember, 43 is equal to 6 times 7 plus 1. So, instead of having this notation, the div and the mod, we can use the floor notation as well, and we get the same thing. So, let's have a look at this. So this is theorem 4.5.3. It's on page 196. It says, if n is any integer, and d is a positive integer, and if q is equal to the floor of n on d, and r is equal to n minus d times the floor of n on d, oh no, that is an n, then, I thought it was just a bad r, but it's actually an n, then n is equal to dq plus r, and naught is less than or equal to r is less than d. Okay, so we've got to prove this. Proof. Suppose n is any integer. Okay, and that's a particular but arbitrarily chosen one. Suppose n is any integer. And d is a positive integer. And q is equal to the floor of n on d, and r is equal to n minus d times the floor of n on d, then dq plus r is equal to d times q, the floor of n on d, plus r, which is equal to n minus d times the floor of n on d. So this is equal to n plus d times the floor of n on d minus d times the floor of n on d. Those can get cancelled. So this is equal to n. Okay, n is equal to dq plus r. We've got it here. All's going well. All we need to show now is that r is between 0 and d. We need to show that 0 is less than or equal to r is less than d. We can have remainder 0, that's when we've got complete multiples. So we know that Q is equal to the floor of n on D. And by the definition, of floor, that means that Q is less than or equal to n on D is less than Q plus 1. Now what we're going to do is multiply everything through by D. So we get dq is less than or equal to n is less than d into q plus 1. Multiplying through by d. Sorry. Me trying to complete it while I'm blowing my nose. Multiplying through by d. Right, so dq is less than or equal to n is less than dq plus d. Now what we're going to do is we're going to subtract dq. So dq minus dq is less than or equal to n minus dq is less than dq plus d minus dq. Subtracting dq. Alright, so dq minus dq is 0, is less than or equal to n minus dq, is less than d. We say, what is n minus dq? That is n minus d times q, which is the floor of n over d. So this is equal to 0 is less than or equal to n minus d, the floor of n on d, because that's what we said q was. And this is just equal to r. 0 is less than or equal to r is less than d, as required. Alright, that's all I wanted to do for 4.5, but as you're probably going to get sick of hearing me say, do the exercises.